Hello and welcome to section 7.1. We're starting a new chapter today. Hopefully, if I do my job right, you guys will see a lot of connections between what we're doing here. Again, we're starting in with exponential functions, specifically exponential growth, and how it actually relates to what we did in the last chapter, which was radicals. Today we're going to actually start out with graphing. Some really unique behavior happens here. We have the invention of something new, something you guys haven't seen before. It's a word that sounds dirty, but it's not. That word that we're going to talk about is an asymptote. Again, that is the word we're looking for here. That's the key vocabulary word, and that's what's going to be new. There's going to be a lot of similarities between what we graph today and what we have graphed in the past. Specifically, shockingly, it's going to be opposite x and same y. So, opposite x, same y is key to graphing, just like it was in the previous chapter, just like it was in chapter 2, just like it was in chapter 3, just like it was in chapter 4. So you're telling me that there's a pattern to all this? Yes. The same thing happens every time. So, we're going to explore that at the very beginning here. Then I'm talking about that word, the asymptote. By the way, that is your key word today. That is the password today, asymptote. So I give it to you at the beginning of the lesson. All right. First off, I'm going to start with where we have been. You do not necessarily need to get these in your notes. In fact, I would encourage you just to follow along as I kind of diagram these on the board. Don't really worry about getting this into notes. Just make sure that you're okay with what's happening on these functions. But first off, I'm going to look at y equals 2x. You should hopefully agree with me. That has a y-intercept of 0 and a slope of 2. So I would go up 2 over 1, up 2 over 1. And I would go ahead and connect those dots in a straight line. Something like that. Oh, that was not very close. Try that again. 0, 0, up 2 over 1, up 2 over 1, up 2 over 1, down 2. And let's try to connect those dots. Better this time. There we go. Roughly speaking, that's a graph of y equals 2x. Graph number 2, which says y equals 2x minus 2. Hopefully you'll agree. That's the exact same graph, same slope, shifted 2 units down on the y-axis. Again, a shift of -2 with the same slope. And again, we've talked about how those lines are parallel. Parallel lines have the same slope. And the similarity between 1 and 2 is that they're the exact same graph. It's just the second graph is shifted 2 units down. This next graph, however, is a bit of a change. It's negative, and then the quantity of 2x minus 2. A lot of you guys say, well, I'm going to distribute that, which is indeed correct, but I want to talk about what's happening graphically here. If I distribute that in, it's going to give me a slope of negative 2x and a y-intercept of positive 2. Okay? So it's going to be something like this. Okay? Again, in that case, we've distributed that through. We're looking at negative 2x plus 2. Again, that's the same graph as number 1 there, except for we've shifted it up 2 units and we've taken the opposite of that slope. It's a negative 2 instead of positive 2. We're going down here where previously we were going up. And we were going up. All 3 of these are very similar. All 3 of these are based off that same red graph, or my original graph. Okay? So make sure you're okay with those similarities on those lines. Again, I don't expect you to copy this all down. I just wanted you to follow that discussion. Next part. We've got parabolas here. Gee, Mr. Wood, this looks very similar to things I know. I know. It's supposed to. We'll start with y equals x squared. That's the easiest form of a parabola. I'll do it in red, like I did in the last one. 0, 0. We're scaled by 2's here. So 1, 1, negative 1, positive 1. We also have the coordinates 2, 4, and negative 2, positive 4. So that parabola was something like that. Next up, y equals the quantity x minus 1 squared. That is the exact same parabola, but we will be shifting opposite x, or positive 1 unit over on our x-axis. That's positive 1 unit shifted over. We'll have the exact same graph, just shifted 1 unit over on the x-axis. Opposite x, same y. And notice that there's no y change on that parabola. Graph number 3, this child is a little bit different than its parent. Again, here's the parent function. Oops, that's the wrong color. Here's the parent function. There's a child, opposite x, same y. Remember, that's your vertex, 1, 2. So our vertex is going to be at 1, 2. It's not going to be kind of hard to see, but then I'm going to have the exact same graph shifted up. Just like that. You should see the similarities out of graphs 1, 2, and 3. They're the same graphs, just moved across or translated on our coordinate plane. Opposite x, same y. Mr. Wood, that's nothing new. I knew that before. It's kind of easy. Good. It's supposed to be. Here's what we're looking at today. And we're looking at 3 functions. Hopefully you'll see that function number 1 is probably, hint, hint, going to be our parent function. Number 2, hopefully you'll think that's going to be the parent function shifted opposite x or 1 unit over on the x-axis. Hopefully on number 3, you think it's going to be the opposite x shifted -1 on the x-axis and same y, +1 on the y-axis. And that's indeed what's going to happen with these 3 graphs. So, start with the parent function because you probably don't have any idea of what these graphs are going to look like. Parent function is always the easiest form of a function. And you might want to go ahead and get these 3 in your notes. So these will probably be the first 3 do down. I'll slow down so you guys can go ahead and catch up here and get those 3 copied down. Probably want to pause the video, actually. Okay, hopefully pause the video. Got those 3 written down. We're going to look at them. We're starting with the parent function. That's y equals 2 to the x. And we're going to start with easy values. Let's see. If I use 0, that's a nice easy value. 1, I think 2. If I use 0 and I click 0 in for x, that says y equals 2 to the 0 exponent. What is 2 to the 0? There's a rule we talked about in the last chapter. Anything to the 0 exponent or anything to the 0 power is always 1. Huh? Okay, I forgot about that, but I remember it now. All right, plugging 1 in for x, that's going to say 2 to the 1. 2 to the 1? 2. Not so hard yet, Mr. Wood. Okay, let's plug in 2 then. If I plug in 2, that's going to be 2 squared, which is 4. I thought you said this was hard. No, I actually never said this was going to be hard. In fact, it's going to be pretty easy today. And if we have those 3 coordinates, that's really all we need, and we can graph this. But before I graph it, remember, this is that parent function. I want to know what happens here. What happens when x is -1? And what happens when x is -2? Well, I think I should just substitute in -1 for x. And that's what you would do. Now my question is, what is 2 to the -1? I recognize that from a different chapter. 2 to the -1, that negative exponent, hey, that's in the wrong spot. That means this thing is in the wrong spot. So actually, 2 to the -1 is 1/2. All right, what happens when x is -2? That says 2 to the -2. That's in the wrong spot. So that's actually going to be 1/4. And again, I'm getting this as 2 to the -2 is the same thing as saying, remember, wrong location, got to move it down, 1 over 2 squared, which is 1/4. It's also how I got the 1/2 there. All right, let's plot these. 0, 1, 1, 2, 2, 4, -1, +1/2, -2, +1/4. kind of different. It looks like it's a curve. We've graphed curves before. My question to you is this. Well, what happens when I have a value of x equals, I don't know, I haven't done it. What about 3? You guys are probably thinking, well, that's 2 cubed. That's 8. So 3/8. Okay. Looks like we're going to keep getting up at that end. What about this? What about if x was equal to negative 10? What do you guys think y would be in that case? Hopefully you guys did this. Well, let's see. Y equals 2 to the x. So that's saying y is going to equal 2 to the negative 10. Well, that's a fraction. That's 1 over 2 to the 10th. 1 over 2 to the 10th, that's a very small number. Isn't 2 to the 10th? 1 over 2 to the 10th is a very small fraction. In fact, over here at negative 10, I'm going to have a number going to be really, really close to 0. And if I have negative 100, that number is going to be super small. There's something weird happening here. Negative 100 still, I know that when I'm getting bigger, like 4, I'm going to get a big positive number there. 6, I'm going to get a big positive number. But some weird things are happening at this negative end. As I keep putting in negative big numbers for x, I'm getting y values that are really, really small. But the catch is, and that's today's dirty word, the catch is I'm never going to get to 0. I'm always going to have a small fraction. So what we do mathematically to represent these small fractions that we have at the negative side, we have this thing called an asymptote. An asymptote is represented by a dashed line. And here's what happens with our asymptotes. Our curve, and this is how we graph this parent function, our curve is going to keep going in this direction, but it's never going to touch that asymptote. So this curve is always going to stay above that asymptote. Now, on the positive side over here, we know it's just going to get really big. In fact, as I plug in 6 into this function, you'll see, if x equals 6, y is going to equal 2 to the 6. Already, that's like 32. So 6, 32, which isn't even on my graph. So we're getting really big over there. That's called exponential growth. And what's really cool about these graphs of exponential growth functions is you can grow your money exponentially. We've talked about that. You've seen the negative side of credit card debt, but we can't grow our money exponentially. So that's where that's going to come into play later. Okay, so we have that asymptote. We kind of see what's happening. Let's look at our other graphs. By the way, your parent function for these, keep it simple. Just use those 3 numbers. Okay? 0, 1, and 2 for exponential growth. 0, 0, 0, 2, and then 2, 4. Okay? If I want to look at graph number 2 now, which is y equals 2 to the x plus 1, hopefully you see the connection with what we did in the last chapter. We've got our parent function here, which is 2 to the x, and all we're going to do is make a child function. The way that this child is going to change. Opposite x, so minus 1 for every x value, and there is no change for y. There's no change for y, so my y values will stay the same. So opposite x, each x value is going to decrease by 1, so 0 minus 1 is negative 1. 1 minus 1 is 0. 2 minus 1 is 1. And as we said, there's no change for my y values. Nothing's changing, so I will keep them the same, 0, 2, and 4. So my blue is going to be my new function. Hopefully you're already seeing that this is going to be the exact same function translated 1 unit to the left on the x-axis. Again, I'm going to do it in blue. -1, 0. 0, positive 2. And 1, positive 4. 1, positive 4. And we're going to go ahead and connect these dots. And we're going to look like we need to get an asymptote here. Hold on just a second while I pause the video. All right. I made a mistake, so I'm going to show you that mistake right now. My red graph is actually plotted correctly. When I erased here, I erased the wrong values. So here's the correct value. And I did talk about it before. I spoke correctly. So if I plug in 0 in our parent function, that's y equals 2 to the 0. Anything to the 0 exponent is 1. So our red coordinate is 0, 1. It is located correctly on my graph. Now, to get my translation over here, I didn't have any changes on my y values. So 1, my coordinate is actually -1, positive 1. So that coordinate was the one that was incorrect for you guys. So make sure you get that change. Okay? So our coordinate is -1, positive 1 there. And there's our graph. At this point, our y values are what's impacted. Our y values, if you look at our asymptote from the parent function in red and the green, the y values is what's restricted. You should agree with me right now when I make the statement. We will not have a domain restriction, but we will have a range restriction. In red, domain and range. Domain equals all real numbers, and my range, y will be greater than 0. It can't touch that asymptote, so it's just greater than. My blue function, my asymptote is again at 0. It is just going to be my red graph shifted 1 unit to the left. Okay? And my domain and range for the blue graph, x is all real numbers, and y is greater than 0. Has to be bigger than the asymptote. Okay? My third graph. And some of you guys can see the patterning and where we're going, because you were good at graphing before. So we're still going to take our parent function, that's the red graph. And now I'm looking at number 3, this green graph. It's going to be opposite x, same y for my translations. So opposite x, which is going to be -1, and same y, which is positive 1. So all my x values will shift to the left 1, and all my y values will go up 1. So starting with the red, 0 minus 1 is -1. Red x values, 1 minus 1 is 0. X2 minus 1 is 1. Notice it's the same change in x that I had in my blue. Those parts matched up. Now I have a bigger change for my y values, which is a change of positive 1. So 1 plus 1 is 2. 2 plus 1 is 3. And 4 plus 1 is 5. So now I'm going to graph that green one. -1, positive 2. 0, positive 3, about here. And 1, positive 5, about there. Now here's what's happening. In this case, my asymptote has shifted 1 unit above. I've gone to +1 for my asymptote. In my green graph, I'll say it again, my asymptote has shifted 1 unit up. So here's what the green graph looks like. Asymptote has shifted up 1 unit. Now I won't have any values of y that are smaller than 1. So again, domain, x equals all real numbers, and range, y is greater than 1 now. Same graphs, same behavior, parent function, shifting. Just like we did with our radicals. Both our square roots and our cube roots, this behaves just the same way. Start with your parent, make the child, plot the child, Don't forget to graph your asymptotes and give me your domain and range. All right. Here's what we got. I wouldn't bother copying a lot of this down. Realize what we have. This is our generic form. That's our multiplier, just like it was for cube roots and square roots. There's our opposite x. There's our same y. Y is vertical, x is horizontal, and that tells us up or down and how much we multiply by. Domain and range are always given to you. It's always opposite x, same y. Your your horizontal asymptote is always given to you with your k value. Okay? Let's go ahead and apply it. I'm not going to do those. I'm going to do these. First graph that we want to look at. Y equals 1/4 times 6 to the x. Y equals 1/4 times 6 to the x. We're going to start with a quick t-chart. Again, I only need 3 values. Oops, I don't want that. We only want 3 values. The catch is start with the parent function. Parent function is the easiest form of the function. That's without any junk on it. So the parent function is y equals 6 to the x. That's the easiest thing for me to do. And I'm going to use the 0, 1, and 2. If x equals 0, then 6 to the 0 is 1. I'll just write there, 6 to the 0. If x equals 1, that's 6 to the 1, which is 6. And if x equals 2, that's 6 squared, which is 36. There's my parent function. Notice that my parent function is a 6 instead of a 2 this time. Next up, we're going to make the child. Hopefully you'll agree with me right now. When we make the child, there is no changes for my x values. There's no change for x. There's nothing connected to the x right here. So there's no change for the x, so every x value stays the same. My y values. I have a multiplier here. That says 1/4 times. So I'll have a 1/4 multiplier. So 1, my y value, 1 times 1/4 is 1/4. My y value, 6 times 1/4 is 6 over 1 times 1/4, which is 6 over 4 as a fraction, which is 3 over 2. Next up, I have 36 over 1 times 1/4, which is going to be 9. 36 over 4 reduces to 9. So those are my 3 coordinates. I'm going to plot them. 0, positive 1/4. Go right about there. 1, 3 halves. 1, 3 halves is 1.5. And then 2, 9. Those are my 3 coordinates. Now, remember my asymptote is talked about with my y change. I had a multiplier, but I had no k value. No k value means my asymptote will be right there at 0. The next example or 2, we will have a shifting asymptote. There's my graph of exponential growth. I've got my 3 coordinates, domain and range. X equals all real numbers, and y is greater than 0. Okay. Parent function translated, domain and range with an asymptote. That's what you're doing the whole day. All right, next problem. Y equals negative 3 times 2 to the x. Y equals negative 3 times 2 to the x. I'll give you guys a second to copy that down. I'm going to start making my parent function. And again, a reminder, my parent function is always the easiest form of the function. In this case, my parent is y equals 2 to the x. We just have a multiplier of negative 3. I'm going to use the same x values, 0, 1, and 2. And when x equals 0 in this case, that will be 2 to the 0. Anything to the 0 exponent is 1. That will be 2 to the 1 for 2. 2 squared, which is 4. Again, notice my parent function is 2 to the x. You should also agree that this problem is just like that last problem. Our multiplier this time is not a fraction, so you guys probably like this problem better. No opposite x for change, no opposite x. Same y, that's a -3 multiplier times -3. So all my x values will stay the same, 0, 1, and 2. And all my y values will be subtracted 3. So 1 minus 3 for -2, 2 minus 3 for -1, and 4 minus 3 for +1. So I've got the coordinate 0, -2, 0, -2, coordinate 1, -1, and the coordinate 2, +1. Did I do something wrong? Oh. I think I made a mistake here. You guys probably caught me when I was doing it. I subtracted 3. What should I have been doing? Hopefully just said multiply by -3. So I'll write that again. 2 times -3. We'll try that again. My apologies there. So I'll give you a second to erase if you were just copying down what I wrote. Hopefully you're thinking I'm supposed to multiply that by -3 because that's correct. 1 times -3 is -3. 2 times -3 is -6. And 4 times -3 is -12. There we go. That's going to get us a little better. Big difference in how this graph is shaped. That would have been a pretty big error for me. So let's plot those coordinates now. I'm going to label everything by 1s here. So I got the coordinate 0, -3. I've got the coordinate 1, -6. And then I've got the coordinate 2, -12, which is pretty much off my graph, like down here. Okay? Once again, I want to explain, no shift for the y's. There's no shift for the y's. So my asymptote is still at 0. But this time my graph looks different. This time it's going down instead of up. You should see that change. I went through my 3 points. And domain, range, x equals all real numbers. Y now is less than 0. By the way, I'm sure you are all shocked to see that when that number is negative, the graph goes down. And when that number is positive, that graph goes up. It's almost as if it's the same thing that happens with the square roots, which is the same thing that happens with the parabolas, which is the same thing that happens with the cube roots. Almost like they all go together. Oh me, oh my, I am shocked to see it. I do not know how I ever got this far without seeing that connection. Maybe. All right. You guys have a checkpoint coming up. Go ahead and pause the video, get that graph down. Just a quick reminder, your parent function is 3 to the x on this one, not 2 to the x or not 6 to the x. So 3 to the x is your parent function. Pause the video, get that bad boy graphed, and then unpause it and we'll move forward. Okay, hopefully you got that thing graphed. Moving on to the next example. Again, I don't need you to do this in your notes, but I want to just kind of do a quick setup so that you understand what's happening in the change before we actually graph them. Again, you've seen some problems. What's going to be the domain or range, or what's going to be the shift? Or looking at this graph, how is it going to change? And that's what I want you to be able to do. We're looking at the graph y equals 5 times 2 to the x minus 1 minus 2. Here's what I want you to be able to tell me. Every single x value, your parent function is 2 to the x. Every single x value will increase by 1, opposite x, and your y values will change by a multiple of 5, and then you'll subtract 2 from it. That's all I want you to be able to tell me. If you can do that, then you can get all this stuff graphed. Mr. Wood, is it really that easy? Uh-huh. You mean if I just do the parent-child every time I'm going to get the right answer? Uh-huh. You mean all I have to do is really add and subtract by these small numbers every time? Uh-huh. So I can do this without a calculator? Uh-huh. Y equals 5 times 2 to the x plus 1 minus 2, the next function here. Parent function, again, is 2 to the x. The change in x is this time is going to be minus 1. It's opposite x. Your change in y is still going to be multiplied by 5 and then subtracted by 2. y equals 3 times 2 to the x plus 2. Again, you don't need to copy this down in your notes. I'm just making sure we're clear. Parent function on this one is 2 to the x. There will be no change in any of my x values. There's nothing connected to that x. My y values will be multiplied by 3 and then added to 2. Lastly, this one, y equals 3 times 2 to the x plus 1. My parent function is 2 to the x. My x values will change by an opposite x. My y values will change by a multiplier by 3 with no additional adding on to. Next piece. Your asymptote on this graph is at 0. Your asymptote on this graph is at -2. Your asymptote on this graph is at +2. And your asymptote on this graph is at -2. Your asymptotes will always be given to you in terms of that k value of your function. Okay? All right, let's do some advanced graphing. First off, 2 times 3 to the x minus 2 minus 2. For this function, start with your parent, make a child. Again, y equals 2 times 3 to the x minus 2 minus 2. I don't want to do that. Hopefully you got this copied down. Y equals 2 times 3 to the x minus 2 minus 2. Hopefully you're agreeing with me that this time your parent function is y equals 3 to the x. My x values for the parent will be 0, 1, and 2. And hopefully you can start doing this one in your head. That's going to be 1, 3, and 9. Next up, how do we change? Opposite x plus 2, same y, multiplied by 2, and then subtract 2. Multiplied by 2, and then subtract 2. Take your x changes first. 0 plus 2 is 2. 1 plus 2 is 3. 2 plus 2 is 4. Your y changes. Multiply by 2, then subtract 2. 1 times 2 is 2. 2 minus 2 is 0. 3 times 2 is 6. 6 minus 2 is 4. Lastly, 9 times 2 is 18. 18 minus 2 is 16. This is the function you're graphing. Don't forget to cover your asymptote. Your asymptote is at -2 here. -2. And plot your points. 2, 0, 1, 2, 3, and 4. 1, 2, 3, 4. And then 4, 16 for me is way off this graph. And there we go. Easy peasy. Domain, x is all real numbers. Range, we have a range restriction. It's given to me in terms of my y values. And y is greater than -2. Easy peasy. Parent function, translate, graph, cover your asymptotes, play doctor. Next function, y equals -3 times 2 to the x plus 4 minus 1. Again, y equals -3 times 2 to the x plus 4 minus 1. You should be able to describe the translations just by looking at it. Opposite x, so -4 for my x. My y is going to be multiplied by -3 and subtracted 1 from that. Also, you should realize that you will have a asymptote at -1. Your parent function y equals 2 to the x. Oops, don't want that guy. So get that parent function. Y equals 2 to the x this time. 0, 1, and 2. 2 to the 0, 1. 2 to the 1 is 2. 2 squared is 4. You've seen that parent function already. Probably you guys are starting to get bored with this because it's kind of easy. It's good that it's easy. It means you're going to get it right. Our changes for x, opposite x, so minus 4. Minus 4 changes for y, times by negative 3, minus 1. Times by negative 3, minus 1. 0 minus 4 for my x value is negative 4. 1 minus 4, negative 3. 2 minus 4, negative 2. Changes for y's. Multiply by negative 3, then minus 1. 1 times negative 3 is negative 3. Minus 1 is negative 4. 2 times negative 3 is negative 6. Minus 1, negative 7. 4 times negative 3, negative 12. Minus 1, negative 13. Plot our points. 4, negative 4 is not on this graph. I'm going to get rid of that graph and get a new graph. Give me a second. There we go, new graph. So 4, negative 4. 4, negative 4. Negative 3, negative 7. And then negative 2, negative 13, which is going to be off this graph also. My asymptote, as I already said, is going to be a negative 1. And all we have to do is connect those dots and play doctor. Domain, all real numbers, range. This time y is going down. It's going to be less than negative 1. Wherever our asymptote is, it's going to be greater than, or it's going to be less than. Okay, you pretty much have graphing exponential functions. You guys got another checkpoint, and then I'm going to do a word problem. There's your checkpoint. Go ahead and pause this video. When you are done with this problem, go ahead and unpause it, and we'll finish it up. It's got about 10 more minutes left. Okay? Okay. Should be finished with that checkpoint. Like I said, a little bit long video today. I'm sorry about that. In fact, actually what we're going to do, just 2 checkpoints today, and I will actually do this problem in class tomorrow. I'll do this problem in class tomorrow. If you'd like to tackle it today or try to attempt it today, you can. I will do this problem during class and we'll explore that. So just 2 checkpoints and you are good to go.